Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1830 witnessed myriad scientific advancements, a period of burgeoning intellectual exploration. Among the significant contributions of that era stands Siméon Denis Poisson's mathematical theory of heat. This work, a testament to Poisson's profound grasp of mathematics and its applicability to the physical world, provided a rigorous framework for understanding heat propagation. It represented a significant leap forward, building upon the foundation laid by Joseph Fourier, while simultaneously charting its own distinct course. The mathematical theory of heat was considerably more than a mere refinement. It was a reformulation, a reimagining of the problem, pushing beyond Fourier's advancements in its own right. To fully appreciate Poisson's contribution, we must first consider the scientific landscape from which it emerged. Prior to Poisson, the study of heat had been largely descriptive, limited primarily to experimental observations and empirical generalizations. Fourier, in his monumental work Théorie analytique de la chaleur, published in 1822, had provided a mathematical treatment of heat conduction. Using the concept of Fourier's series, he was able to propose solutions to the heat equation for various geometries and boundary conditions. Fourier's work, particularly the elegant application of what would become Fourier analysis to heat transfer problems, was revolutionary. It offered a powerful tool for solving complex problems involving heat diffusion. However, Fourier's approach, while innovative, faced certain challenges. His analysis relied on the assumption that the initial temperature distribution could be represented as a sum of trigonometric functions, a constraint that could be problematic. Poisson's goal involved addressing some of the imperfections while extending the theory. Poisson's mathematical theory of heat built upon and, in some respects, diverged from Fourier's. Poisson, like Fourier, embraced the mathematical power of partial differential equations to model heat flow. Poisson's work aimed to extend Fourier's model and explore some of the limitations. He provided alternative derivations, explored different boundary conditions, and delved into the behavior of heat in various media. A central aim was the examination of heat diffusion in inhomogeneous bodies, a consideration absent from Fourier's primary formulation. Poisson was particularly interested in the relationship between the initial conditions and the subsequent temperature distribution. At the heart of Poisson's theory was the heat equation, a partial differential equation that describes how temperature changes over time and space. The heat equation, in its simplest form, states that the rate of change of temperature at a point is proportional to the Laplacian of the temperature at that point. In one spatial dimension, this is expressed as the partial derivative of u with respect to t equals alpha times the partial derivative squared of u with respect to x squared, where u represents the temperature, t the time, x the position, and alpha the thermal diffusivity. Poisson did more than simply restate the equation. He explored it with meticulous rigor. He focused on solving the heat equation for specific scenarios, employing techniques like the method of separation of variables and integral transforms, techniques that had been pioneered by Fourier. He meticulously addressed the details of boundary conditions. He explored different types of boundary conditions, such as a fixed temperature, the boundary, or a heat flux proportional to the temperature gradient. Furthermore, also investigated the problem's implications for understanding the distribution of heat in solids, a problem with profound implications for understanding materials science and engineering. Poisson's mathematical prowess revealed itself in his meticulous analysis of the heat equation's solutions. He showed how the solutions could be obtained for various initial and boundary conditions, a feat of mathematical skill and deep physical insight. This allowed for the modelling of a wide array of heat transfer problems, including the cooling or heating of objects, the distribution of heat in complex geometries, and the study of thermal properties of different materials. Poisson's analytical approach provided a robust framework for tackling the real-world problems that Fourier had pioneered earlier. The theory possessed the flexibility to adapt to an array of diverse conditions. The theory also offered a framework for exploring different physical systems and their thermal behavior. The immediate impact of Poisson's work was considerable. It refined and expanded the mathematical tools available for studying heat conduction. His detailed analysis and comprehensive solutions provided a more complete understanding of heat propagation, offering scientists and engineers a more powerful toolkit for tackling practical problems. It reinforced the importance of mathematical modeling in the physical sciences. The approach offered scientists and engineers a means for accurately representing real-world phenomena, enabling a level of precision impossible with mere experiments alone. The mathematical theory of heat was immediately recognized for its thoroughness. The influence of Poisson's work extended far beyond its immediate applications. It paved the way for subsequent developments in heat transfer theory and other areas of physics. His meticulous mathematical treatment served as a model for others, influencing the way scientists approached other complex physical problems. Specifically, his careful attention to boundary conditions and initial conditions became a standard practice. Later generations of scientists built upon his approach. His careful treatment of the heat equation was a model that has inspired scientific innovation. Poisson's work was also viewed critically, a testament to its significance. Some criticisms focused on the complexity of his mathematical formulations, which occasionally made them difficult to apply in practice. Others pointed to the limitations of the heat equation itself, which, while accurate for many situations, did not account for all the complexities involved in heat transfer. However, these criticisms did not diminish the value of Poisson's contributions. Rather, they spurred further research and refinement of the theory. The critiques provided an incentive for scientists to improve the formulation of the heat equation and expand its range of validity. Poisson's mathematical theory of heat directly influenced many subsequent thinkers. His work provided a foundation in the study of heat that others were able to build upon. His work influenced the development of thermodynamics. He contributed to the development of the mathematical tools, such as partial differential equations, that would become essential for later generations of physicists and engineers. His meticulous analysis of the heat equation helped to clarify the connection between the abstract mathematical model and the observable physical world. Poisson's detailed solutions provided a solid framework for addressing heat transfer problems and inspired the development of more advanced numerical methods. The evolution of heat transfer theory in the aftermath of Poisson's work reveals its enduring legacy. The mathematical methods he employed, such as the separation of variables and integral transforms, became standard techniques in the study of partial differential equations. These techniques continue to be used to solve complex problems in physics, engineering, and other fields. Furthermore, his emphasis on boundary conditions and initial conditions had a lasting impact. This encouraged many physicists to carefully consider the physical context of the mathematical models they used. These elements have become cornerstones of modern scientific practice. Poisson's contributions were also directly inspired by a constellation of predecessors. Fourier's theory analytique de la chaleur was the obvious primary influence. It established the mathematical framework for studying heat conduction. Poisson built upon Fourier's foundation. He addressed limitations and provided alternative solutions. The work of Joseph-Louis Lagrange and Pierre-Simon Laplace, who pioneered the use of partial differential equations in physics, also provided the mathematical groundwork for Poisson. They refined mathematical tools central to Poisson's approach. Poisson himself built upon the mathematical models of his predecessors to arrive at his theory. The work, in turn, exerted a profound influence on future generations of scientists and engineers. His mathematical approach, his attention to detail, and his relentless pursuit of accurate solutions served as a model for others. His work spurred the development of more sophisticated models of heat transfer. His methods were applied to understand diffusion processes outside of the realm of heat transfer. His elegant application of mathematics to physical problems inspired scientists and engineers across multiple disciplines. The work of Poisson has had a remarkable impact on mathematical research and scientific progress. His work remains critical into the 21st century. In conclusion, Siméon Denis Poisson's mathematical theory of heat, published in 1830, was a remarkable achievement. It built upon previous work, particularly Fourier's, while also forging its own path. His mathematical prowess led to elegant solutions of the heat equation, offering a comprehensive understanding of heat propagation. The work refined the mathematical tools for studying heat conduction and set a standard for later generations of scientists. His rigorous approach to boundary conditions and initial conditions, the enduring legacy of his work, transformed the field. Poisson's mathematical theory of heat was more than a mere refinement. It was a reimagining, a reinterpretation, a profound leap forward in our understanding of the physical world. The work continues to impact our world today.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.